Hello everyone, welcome to lecture on Design of RC Elements. Myself M. Dinesh Kumar, Assistant Professor, Department of Civil Engineering, Hindustan College of Engineering and Technology, Coimbatore. In this video, we are going to design a RC beam by using limit state method based on one problem. A reinforced concrete beam is to be designed over an effective span of 5 meters to support a design service load of 8 kN per meter. Adopt M20 grade of concrete and Fe415 HYSD bars and design the beam to satisfy the collapse and serviceability limit states. In this problem, we are having a effective span of 5 meter. So L is equal to 5 meter. And our grade of concrete is M20. For M20 grade of concrete, the characteristic compressive strength F suffix CK is equal to 20 Newton per mm squared. And also we are having a grade of steel is Fe415. For Fe415 grade of steel, Fy value yield tensile stress value is equal to 415 Newton per mm squared. And also we have a design service load of 8 kN per meter. So these are the given data. So you want to design a reinforced concrete beam based on collapse and serviceability limit states. So first we have to find the cross-sectional dimension of our beam. So you want to assume L by D ratio, the span to the effective depth ratio. Since our live load is very large, that is live load value is equal to 8 kN per meter. So since the live load value is very large, so we are assuming F span divided by effective depth ratio is equal to 15. So the effective span value is equal to 5 meter in terms of mm, 5000 mm, right? So 5000 divided by 15, we can get the value of effective depth of our span beam equal to 333 mm. So the overall depth of the beam is equal to small d plus d dash, where d dash is equal to effective cover. So the effective cover required for the beam section is 50 mm. So overall depth is equal to effective depth plus effective cover. So 350 plus 50, the total value is equal to 500 mm. So we want to adopt the width of our beam section. So we adopt the width of the beam section is equal to 200 mm. So our size of the beam is equal to small b into capital D. The size of the beam small b by capital D. So that is 200 mm by 400 mm. So this is our size of beam. Then next we have to calculate the load on the beam. So first we want to calculate the self weight of our beam. So self weight of beam is calculated by using the formula small b into capital D into unit weight of concrete. So we are using reinforced cement concrete. For reinforced cement concrete, the grade gamma C, that is unit weight of concrete RC concrete, is equal to 25 kilonewton per meter cube, where B is equal to 200 mm and D is equal to 400 mm. Gamma C is equal to 25 kilonewton per meter cube. So the dimensions are in meter. You have to convert all the dimensions are in meter. So 200 mm is equal to 0.2 meter. 400 mm is equal to 0.4 meter. So 0.2 into 0.4 into unit weight of concrete is equal to 25. So we get the self weight of the beam is equal to 2 kilonewton per meter. So as per our question, live load value is given. So the live load is equal to 8 kilonewton per meter. So the total load is equal to self weight of the beam plus live load. 8 plus 2 is equal to 10 kilonewton per meter. So this is a working load. We are adopting a limit state concept. For the limit state concept, we will have to calculate the value of ultimate load. So the partial safety factor based on the limit state method is 1.5. So the ultimate load formula is equal to 1.5 into working load. So 1.5 into 10 kilonewton per meter. So the ultimate load is equal to 15 kilonewton per meter. Next, we have to calculate the ultimate bending moment and shear force. So let us assume our beam is a simply supported beam carrying UDL. So the load in terms of kilonewton per meter. So our beam is simply supported carrying UDL. If your beam is simply supported carrying UDL means the ultimate moment formula is equal to WU LE square divided by 8. So the WU value is equal to 15 kilonewton per meter. L is equal to effective length is equal to 5 meter. So 15 into 5 square divided by 8. So the ultimate bending moment is equal to 46.8 kilonewton meter. So the shear force, ultimate shear force can be calculated by using the formula WULE divided by 2 because our beam is simply supported beam carrying UDL. The formula is equal to WULE divided by 2. So WU value is equal to 15, LE is equal to 5. So 15 into 5 divided by 2, the value of ultimate shear is equal to 37.5 kilonewton. Next, we have to identify our section whether it is under reinforced or over reinforced. For that, we have to calculate the value of limiting moment. So our grade of steel is Fe415. For Fe415 grade of steel, the limiting moment formula is equal to 0.138 FCK BD square. FCK is equal to characteristic compressive strength of concrete. Our grade of concrete is equal to M20. So for M20 grade of concrete, F suffix CK value is equal to 20 Newton per mm square. So here the value of FCK in terms of mm square, Newton per mm square. So all the values we have to substitute in terms of mm. So B is equal to breadth of the beam is equal to 200 mm. D is equal to effective depth value is equal to 350 mm. So substitute all this value, we can get the value of mu limit is equal to 68 into 10 to the power 6 Newton mm. In order to, in terms of kilonewton per meter, 1 into 10 to the power 6 Newton mm is equal to 1 kilonewton meter. So 68 into 10 to the power 6 is equal to 68 kilonewton meter. So this value is greater than the this value is greater than the our moment 46.8. Hence our section is under reinforced section. So your section going to be designed as an under reinforced section. Next, based on our bending moment calculation, we have to find out the required AST, that is reinforcement details for that moment. As per IS 456-2000, page number 96, class G 1.1.C, for the under reinforced beam section, the mu is equal to 0.87 Fi AST D into 1 minus Fi AST divided by FCK BD. By using this formula, we can find out the value of AST, area of a tension steel reinforcement. So here in this formula, mu is equal to ultimate moment is based on our loading calculation. Then Fi is equal to yield tensile stress and AST equal to area of a tension steel reinforcement, and small d is equal to effective depth. Then Fy is equal to yield tensile stress of steel, B is equal to breadth of the beam, and D is equal to effective depth, FCK is equal to characteristic compressive strength of our concrete. We already have all this value except AST. By substituting all this value, we can get the value of AST is equal to 425 mm square. Then we want to assume the diameter of the bar. So let us assume 12 mm dia bar as a main reinforcement. So we want to calculate the required number of for this moment. Then N is equal to capital AST divided by small AST. The capital AST is equal to 425 mm square. Small AST can be calculated by using the formula of pi d square divided by 4. Here d is equal to the diameter of the bar, that is diameter of bar is equal to 12 mm, that is 3.14 into 12 square divided by 4. Then small AST is equal to 113.04. The number of bars equal to capital AST divided by small AST. Then the required number of bar is equal to around 4 numbers. So you have to provide 4 numbers of 12 mm dia bar as a tension reinforcement. In order to support the tension reinforcement, we have to provide another 2 numbers of 10 mm dia bar as an hanger bars on the compression side, because we are having an under reinforced condition. For the under reinforced condition, our beam is a singly reinforced section. Then we cannot provide the main reinforcement at the compression side. So you have to reduce the diameter of the bar to 10 mm to support these tension reinforcements. Then next we have to check the shear. For the check for the shear, we have to find the two values. So first value is tau suffix v and second value is tau suffix c. So the tau suffix v, that is nominal shear, is calculated by using nominal shear stress can be calculated by using the formula of Vu is tau v is equal to Vu divided by B into D. So Vu, as per our calculation of shear and shear calculation, so our shear is equal to 37.5 kilonewtons and B is equal to 200 mm, D is equal to 350 mm. So you have to calculate the value in terms of Newton per mm square. So that's why we have to substitute the shear value in terms of Newton. 1 kilonewton is equal to 10 to the power 3 Newton, that is 37.5 kilonewton is equal to 37.5 into 10 to the power 3 divided by 200 into 20. So the tau v, nominal shear stress, is equal to 0.53 Newton per mm square. Then we have to calculate the value of design shear stress, that is tau suffix c, is based on table number 19 of IS 456-2000, page number 73. So for that you have to calculate the value of percentage of reinforcement, that is P suffix T, that is 100 AST divided by BD. So AST is already calculated, then B is equal to 200 mm, D is equal to 350 mm. The percentage of steel reinforcement is equal to 0.465. By use, so based on the value of percentage of tension reinforcement P suffix T and grade of concrete, our grade of concrete is equal to M20. So our percentage of steel reinforcement is equal to 0.625, right? So based on table number 19 of IS 456-2000, 0.625 is lies between these two values, right? Between 0.5 and 0.75. So the tau suffix c value is between 0.8 and 0.56. By interpolating these two values, you can get the value of tau c. So for a percentage of tension reinforcement 0.645, grade of concrete M20, based on the interpolation tau suffix c based on table number 19 of IS 456, tau suffix c is equal to 0.51 Newton per mm square. Hence tau suffix v is greater than tau suffix c. So based on page number 73 IS 456, the shear reinforcement is required. Okay. So based on IS 456, page number 73, in order to provide a vertical stirrups, so the spacing can be calculated by using this formula. VUS is equal to 0.87 Fi ASV D divided by SV. Here SV is equal to spacing for stirrups. Then ASV is equal to area for the stirrups. VUS is equal to balancing moment. Hence, the balancing moment is calculated by using this formula. VUS is equal to VU minus tau C B suffix T. So this formula, these two formulas also available in page number 73 of IS 456-2000. Where VU, we already have the value of VU and we already find out the value of tau C and we already have the value of B and D. So by substituting all these value, you can get the value of VUS. So VUS is equal to VU minus tau C B into D. By substituting the value of VU and tau C, B and D, the balancing moment is equal to 1.8 into 10 to the power 3 Newton. In terms of kilonewton, 1.8 kilonewton. So comparing the nominal shear, that is V suffix U, that is ultimate shear, the balancing shear is very small. So as the balance shear is very small, so provide the stirrups of 6 mm dia and the spacing is given by 0.775 times D. So 0.75 into the FAT depth is equal to 350 mm. The spacing of the stirrups is equal to 262.5 mm. So hence provide 6 mm dia of stirrups at 250 mm center to center distance. The next we have to draw the reinforcement details based on the result we arrived. So our effective span is equal to 5 meter At the tension zone, we have to provide 4 numbers of 12 mm dia bar. Then at the top of the compression side, we have to provide 2 numbers of 10 mm dia as a hanger bars. Then we have to provide the secondary reinforcement as 6 mm dia at, that is a shear reinforcement, 6 mm dia at 250 mm center to center distance. Then our overall depth of the beam section is equal to 400 mm. Then effective depth, that is top surface to the center of bottom reinforcement, is called effective depth small d. Small d is equal to 350 mm. Then the breadth of the beam is equal to 200 mm. So these are the reinforcement details. So this is the way to design your RC beam by using limit state method. Thank you.